So in this video we're going to apply the fundamental theorem of calculus in an example involving a polynomial. So it says find the area given by the integral from 1 to 4 of negative x squared plus 6x minus 3. So we have a definite integral being applied to a second degree polynomial. So we are trying to calculate the integral from 1 to 4 of negative x squared plus 6x minus 3 dx. And the fundamental theorem of calculus says that the first thing to do is not worry about the bounds of integration, but just find an antiderivative for f of x. So big F of x is just any antiderivative. So we could actually directly calculate this antiderivative right here. Or if you prefer, we could break it up into individual pieces using properties of integrals. So one possibility would be to take this and say, I'm going to break it into the individual integrals. So the negative x squared, I could rewrite that as the opposite of the integral of x squared dx. And I would still be evaluating from 1 to 4. Plus, here's a 6x, so 6 times the integral from 1 to 4 of x dx minus, and then 3 times the integral of dx from 1 to 4. So one way we could do it is just break it up into the pieces. And then for each of the pieces, try to find an antiderivative. So for this first piece, it would be negative. And then the antiderivative of x squared is 1/3 x cubed plus 6 times the antiderivative of x is 1/2 x squared. But 6 times 1/2 is just 3, so we get 3x squared right there. And then we get minus, and then the antiderivative of 3 times the antiderivative with respect to dx is just going to be minus 3x. And then once we have an antiderivative, which right here we have an antiderivative for the original second degree polynomial, once we have the antiderivative, we put the vertical bar here. So we want to follow the notational standards, put the vertical bar, and tell the reader that we're integrating this from 1 to 4, or evaluating this from 1 to 4. Once we've done that, then the next step is to put the upper bound of integration into the antiderivative. So I'm going to go down here and go negative 1/3 times 4 cubed. So this upper bound of integration going in for the x cubed. So negative 1/3 times 4 cubed plus 3 times 4 squared minus 3 times 4. And then we go minus, and I need to put a parenthesis so that I'm sure to distribute my minus sign into what comes next. And what comes next needs to be my lower bound of integration input into my antiderivative. So I'm going to take the 1 right here and put it into my antiderivative everywhere I see an x. So I'm going to get negative 1/3 times 1 cubed plus 3 times 1 squared minus 3 times 1. And then we just need to simplify. So there's a lot of different ways of working on simplifying it. I'm going to factor a 12 out of each of these terms. So I'm going to do a 3 times 4 is 12 and factor it out. And if I do that, right here, I'm going to change this 1/3 into a 3/9, which is still a 1/3. So if I factor out a 12, which is 3 times a single 4, that's going to leave behind a negative. And I factored a 3 times 4 out, so a 4 squared is left behind, so 16/9. I factored a 12 out, so I factored out a 3 times 4, which will leave behind a single 4. And I factored out a 12, which will leave behind a minus 1. And now I can distribute the minus sign here into the parentheses, so I get a double negation is a plus. 1/3 times 1 cubed is a 1/3. Negative, positive, negative. 3 times 1 squared is 3. Negative, negative, positive. 3 times 1 is 3. And then we just start simplifying. So I get 12 times. And right here I have negative 16/9 plus 4 minus 1 is 3. But 3 is really the same as 9 over, let's see, 27. Sorry, I had plus 3. So I want to change that to 27 divided by 9, which is still 3, which gives me my common denominator. And then here, minus 3 plus 3 will cancel, giving me a 0. So I just get plus a third. And then I can continue to simplify. So I have 12 times negative 16 plus 27 is 11. And this is over a 9 plus a 1/3. But 1/3 is the same as 3/9. So I want to write it with that common denominator. And here, 12 is the same as 3 times 4. So I'm going to rewrite this numerator here as 3 times 44. So this is 3 times 44 plus 3 over my denominator of 9. And 3 44 times plus one more 3 is the same as, I'm going to bring my work up here, 3 times 44 plus 3 times 1 is 3 times 45 over 9, but 9 goes into 45 5 times, so 3 times 5 is 15, which is the area under the curve. Now here it says use your graphing calculator to verify the result, which I did beforehand, so I would have a check on my work. In the next video, I'm going to show how to use GeoGebra to produce this calculation. So you can use GeoGebra in order to check your work when you're working with definite integrals.